about that. We'll get this thing running. Yeah, usually I have this all ready to go, but for some reason, a lot going on today. Got there anyway. Plug this in. Yeah, we're just waiting for it to load. Yeah, wait. Let's see what happens. Lost in Life asks, what is it live about? Well, it might be about artificial intelligence, a self-study course, if it wants to load. Having little problems here.
Okay, let's unpack this. Have you ever really stopped to consider the invisible intelligence shaping your world? It's everywhere now, isn't it? I mean, from the moment you wake up, ask your smart speaker about the weather, or, your streaming service suggests your next binge, or even your car, maybe helping you parallel park. AI. It felt like sci-fi for so long, but now it's just, well, it's woven into daily life, often in ways we barely notice.
It really is. And, what's truly fascinating here is that while AI feels incredibly new, its fundamental roots go back surprisingly far. The complexity, it can seem daunting, right? Like trying to decipher an alien language. But it really does start to make sense once we break it down to its core principles, first principles, really.
Right.
And today, that's exactly our mission. We're using this excellent AI self study course outline as our guide. Think of it as a really well drawn map for navigating this huge landscape.
Yeah. And our mission for this deep dive is clear. We want to give you a structured, concept by concept understanding of AI. We're going to cut through the jargon, distill the essence, basically offer you a shortcut to being genuinely well informed about this whole AI revolution. We'll journey from its ancient, almost mythical beginnings all the way to the cutting edge generative models making headlines practically every day. Expect some surprising facts, hopefully a few insights that spark those aha moments, and practical takeaways too, to help you grasp the underlying why behind it all. So let's dive in.
The genesis of AI, a journey through time and ambition.
So, okay, where do we even begin talking about artificial intelligence? It might surprise you that the idea of intelligent machines isn't modern at all. Long before microchips, even before electricity was widespread, people were dreaming up automatons, mechanical figures with some kind of artificial life or intelligence.
Like those ancient Greek myths,
Yep.
statues that could move.
Exactly, or those super elaborate clockwork figures from the Renaissance. They weren't AI, as we think of it, obviously, but they were like the earliest conceptual seeds. Philosophical thoughts about what it means for something non-human to act intelligently.
So the idea is ancient.
Right, but the formal scientific pursuit, the kind that led us here, that's really a 20th century thing, kicked off in large part by World War II.
Indeed. Yeah, the groundwork for modern AI was truly laid in the 1940s and 50s. A really pivotal early moment, though maybe not AI by our current definition, was Alan Turing's work during the war. In 1942, he and his team designed the bomb machine. Its job was cracking the German Enigma code.
Ah, the Enigma machine.
And its significance was just profound. You had a machine performing a highly complex cognitive task of cryptanalysis at superhuman speed. It didn't learn, but it showed the sheer potential of machines for tackling problems previously thought uniquely human. What machines could do.
And Turing, well, he didn't stop there. In 1950, he asked that huge question: can machines think? To explore it, he proposed the imitation game.
Yeah.
We all know it now as the Turing test.
Right, the classic test.
Imagine you're texting with two hidden players, one's human, one's a computer. If you, the judge, can't reliably tell which is which just from the conversation,
Yeah.
well, the machine passes. It set a practical benchmark, didn't it? Moving away from philosophical definitions of thinking towards something you could actually, test. Like a party game where you can't tell who you're texting.
Exactly, and the idea of machine learning, that wasn't far behind either. In 1952, a computer scientist named Arthur Samuel developed a checkers program. The real breakthrough wasn't just playing checkers, it was its ability to learn from its own mistakes. It got better over time. Eventually, it played better than Samuel himself.
Wow, better than its creator.
Yes, it was one of the first and definitely one of the most successful examples of machine learning independently, a real cornerstone concept for modern AI. It showed machines could improve, not just execute.
Okay, so you've got Turing, Samuel, all this brain power bubbling up, and it led to this summer workshop that really changed everything.
That's right. Dartmouth College, 1956. Small group of pioneers led by John McCarthy. That conference is where the field of artificial intelligence was formally born. They actually coined the term there.
They named it.
They named it. And their conviction, laid out in the proposal for the workshop, it was just astounding for the time. They basically said, every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it.
That's incredibly bold for the 50s.
Hugely bold.
Yeah.
That event really marks the official start of AI as its own dedicated research field. The decades after that, say the 60s through the 80s, saw a lot of activity. Some significant early successes too. We got the LISP programming language, which became important for AI. Unimate, the first industrial robot, showed up on assembly lines.
Right, practical applications starting.
And Eliza, the first chatbot. It was simple, really just rephrasing statements as questions. But it created this surprisingly convincing illusion of understanding for a lot of people, hinting at the potential.
But, with that early excitement came some really big promises that didn't quite pan out, right?
That's putting it mildly.
Yeah.
The sheer complexity of real-world problems was massively underestimated, and the computers back then just not powerful enough.
So that led to the famous AI winters.
Exactly. Roughly 74 to 80, and then again from 87 to maybe 94. Government funding, corporate sponsors, they got disillusioned. The money just dried up. Research slowed right down.
Like the hype train ran out of steam and everything froze up.
That's a good analogy. Yeah, it's a crucial lesson, actually, about the cycle of tech hype. Managing expectations is key.
But AI seems to have this resilience. It always bounces back.
It does. The 90s to the 2010s saw a resurgence, often with a more, let's say, pragmatic, data-driven focus. Less about coding explicit rules, more about systems learning from data. And one of the most public milestones, everyone remembers this, was 1997. IBM's Deep Blue beat Garry Kasparov, the world chess champion.
Oh, yeah, huge news. Chess seemed like the ultimate test of human intellect.
Immense strategic complexity. Deep Blue showed the raw power of computation for searching through massive possibility spaces.
And then practical stuff started creeping into our homes more. Roomba, the robot vacuum, in 2002.
Bringing AI right into the living room.
Then the voice assistants. Siri in 2011, Alexa in 2014. Suddenly we're talking to our AI.
Embedding it even further. But maybe an even more critical victory, signaling a sort of deeper shift, was in 2011, another IBM system, Watson, competed on the quiz show Jeopardy! And beat the best human players.
Right. That felt different from Deep Blue somehow.
Very different. Deep Blue mastered a structured game, clear rules. Watson had to understand natural language, nuances, puns, ambiguities in the questions, then find precise answers in this massive sea of unstructured text. That signaled a major shift towards AI that could process and sort of understand human language at scale, a huge cornerstone for where we are now.
And that brings us pretty much up to date. The deep learning era starting around 2012.
Exactly. This current AI boom was really ignited by breakthroughs in deep learning using neural networks with many layers. The Big Bang moment, arguably, was the AlexNet victory in the 2012 ImageNet competition.
Images recognition, right.
Yes. This deep convolutional neural network just crushed the previous error rates. It stunned the research world. And it happened because of this perfect storm. A huge data set, ImageNet, a powerful algorithm, and crucially, using GPU's graphics cards for massive parallel processing.
All the pieces finally clicked.
It really did.
Okay, here's where it gets really interesting, I think. Building on that success, the focus shifted. Not just classifying things, but actually generating things.
Precisely. A move from prediction to generation. In 2019, OpenAI released GPT-2, a large language model that could generate remarkably coherent text. Then GPT-3 in 2020, even more powerful.
But it was ChatGPT in late 2022 that just blew the doors open for the public, right?
Absolutely. Suddenly, millions of people could directly interact with a system that could write essays, generate code, answer complex questions, all conversationally.
It spurred this whole new wave. Models generating images, music, video.
Exactly. So if you look at this whole history, this roller coaster, what do you see?
Well, breakthroughs. Then engineering, then hitting wall.
Right. Conceptual leaps followed by scaling, often limited by compute power or data. The current era is defined by smashing through those limits. If we connect this to the bigger picture, the AI history isn't a straight line, it's ups and downs. But each dip, each AI winter, led to a stronger climb, usually by overcoming some fundamental technical bottleneck.
So the lessons from the winters are important.
Crucial. They remind us to distinguish foundational progress from temporary hype. Always ask. Is this a real step forward or just noise?
Defining intelligence. The AI spectrum.
That historical ride is a perfect setup because now we need to nail down what artificial intelligence actually means. It's not just one thing, is it? It's more like a spectrum, different levels of ability.
That's a great way to put it.
Like skill levels in a game, maybe, or different gears in a car. You would expect first gear performance in fifth gear. Not all AI is the same.
Precisely. And if we break it down using first principles, the field generally distinguishes between 3 levels based on capability and ambition. You have weak AI, strong AI, and then artificial superintelligence. Let's start with weak AI, also called narrow AI. Now, this is important. Weak AI is the only form of artificial intelligence humanity has successfully built so far.
Okay, the only kind we actually have.
Right. By definition, it's AI designed and trained for a specific narrow range of tasks. Think about things like speech recognition, image classification, playing chess. These systems can often perform their specific task with superhuman speed or accuracy. But, and this is key, they operate strictly within a predefined, limited context. They lack general cognitive abilities, they don't have consciousness or self-awareness.
So they simulate intelligence for one problem, but don't possess it generally.
Exactly. It simulates, it doesn't possess in a general sense. And examples are everywhere now. Siri, Alexa, Google Assistant, classic weak AI. They understand voice commands, search info, but can't reason outside their programming.
Right. My smart speaker can't debate philosophy.
But probably for the best. Self-driving car AI. Sophisticated perception and navigation, but it can't compose music or play Go.
Deep Blue, we mentioned. Brilliant at chess, evaluating millions of moves. Couldn't apply that to, say, military strategy.
Recommendation engines on Netflix or Spotify. Weak AI. Trained specifically to predict your taste. Even your email spam filter, highly specialized, weak AI. Its power is automation, efficiency, accuracy within its narrow domain. But it's confined.
So your car's AI drives you to work, but can't tell you a joke about why the chicken crossed the road.
Perfectly put. It excels at one thing.
Okay, so moving up the spectrum, strong AI, also known as artificial general intelligence, or AGI.
Right. Now, this is purely theoretical at this point.
Theoretical, got it.
AGI refers to an AI that would possess intelligence on par with a human being, not limited to one task. It could understand, learn, apply knowledge across a huge range of domains, just like a person.
So what would that look like? What are the characteristics?
Well, you'd expect general cognitive abilities: reasoning, problem solving, planning, abstract thought. Like us, it would likely need consciousness and self-awareness, the ability to reflect on itself, adaptability, learning from experience, handling totally new situations without needing explicit reprogramming, and maybe the trickiest parts: human-like creativity and common sense, understanding social context, emotions.
Okay, that sounds far off.
It absolutely is. It's crucial to stress. Strong AI is purely theoretical. No system today comes anywhere close. Replicating human general intelligence, consciousness, common sense, the challenges are just immense. It's the long-term North Star for many researchers.
So when we see robots in movies like Wall-E or Big Hero 6, that's often what they're portraying, AGI.
Often, yes. They're illustrating what strong AI might look like if we ever achieved it.
And then at the very top of this hypothetical pyramid, artificial superintelligence, ASI.
Even more hypothetical, ASI is the idea of an AI that wouldn't just match human intelligence, but significantly surpass it in virtually every field: scientific creativity, general wisdom, social skills, you name it.
So if AGI is human level, ASI is vastly superior.
That's the concept. And obviously, since we haven't even reached AGI, ASI is even more speculative. Now, we should clarify. Narrow superintelligence exists. A calculator is superintelligent at arithmetic. Deep Blue is superintelligent at chess.
But only in that one specific task.
Exactly. That's not generalized superintelligence, ASI. That's a whole different level.
So why does this distinction, weak, strong, super, matter for us, for you listening?
Well, it's really about managing expectations and understanding context. When you hear about some new AI breakthrough, knowing if it's a better form of narrow AI or some claimed step towards AGI helps you gauge its real impact and its potential risks.
It helps separate the science facts we have today from the science fiction speculation about tomorrow.
Precisely. Context is everything here.
The ethical imperative, bias, transparency, and societal impact.
Understanding that spectrum is vital, but we absolutely have to talk about the ethics. AI development isn't neutral. It's not just code. It's deeply tied to societal values, and it has profound consequences.
Yeah, that's a critical point.
Which raises the big question: if AI is getting so powerful, how do we ensure it's used responsibly, for good? Responsible AI practice means being acutely aware of the ethical challenges, the fairness, the accountability, the impact on people. You can't just chase performance metrics.
And one of the biggest ethical challenges right now is algorithmic bias. Yeah, fairness, transparency. The simple, maybe scary truth is AI learns from data. And if that data reflects existing societal biases, racism, sexism, whatever the AI, will learn those biases.
And worse, it can amplify them.
Right, like an AI student who only reads a biased textbook is going to parrot those biases back, maybe even louder.
Exactly. And bias creeps in at multiple stages. The most common is probably data bias. If your historical data reflects systemic inequalities, the model trained on it will inherit them. Think about an AI recruiting tool. Trained on past hiring data from a company that mostly hired men, it might learn to favor male candidates, even if gender isn't explicitly fed in.
Wow.
Then there's algorithmic bias. Sometimes the design of the algorithm itself can introduce bias. Certain models trained on unbalanced data might just naturally favor the majority group, performing worse for minorities. And of course, human bias. These develop themselves as humans. We have our own conscious or unconscious biases that can slip into design choices, feature selection, even how we define success for the model.
And this isn't theoretical, right? This has real world consequences. We've seen examples.
Unfortunately, yes, significant harm. In finance, biased algorithms have unfairly denied loans to qualified people from minority groups, perpetuating inequality.
Okay.
In criminal justice, predictive policing systems, trained on historical arrest data that might reflect biased policing. Well, they've been accused of disproportionately targeting minority communities.
That's deeply concerning.
In healthcare, AI diagnostic tools showing racial bias, higher error rates for certain groups because the training data wasn't representative, leading to potential misdiagnoses, worse health outcomes.
We've seen it in hiring too, right? Facial recognition errors for women, people of color, resume screeners penalizing female candidates.
All documented examples. These aren't edge cases, they affect real people's lives and opportunities, which leads directly to the need for transparency, often talked about as explainable AI or XAI.
Because these models can be black boxes. We don't know why they made a decision.
Exactly.
Yeah.
Especially deep neural networks, it can be incredibly hard to trace the reasoning. And that's a huge problem, ethically and practically. If you're denied a loan by an AI, you deserve an explanation, right?
Absolutely.
XAI is the whole field dedicated to making AI decisions more interpretable, more understandable to humans, cracking open that black box.
So, how do we fight this bias? What are the mitigation strategies?
It's a multi-pronged approach, no silver bullet. Probably the most critical step is ensuring diverse and representative data for training. Garbage in, garbage out. Bias data in, bias model out.
Makes sense.
We also need rigorous fairness audits, regularly checking AI systems for bias using quantitative metrics before and after deployment.
Right.
There are also technical bias mitigation techniques, things like reweighting data to balance groups or adding fairness constraints directly into the model's training objective.
And documentation. Accountability.
Crucial. Creating clear documentation, sometimes called model cards, detailing the training data, performance metrics, limitations, intended use, and establishing clear lines of responsibility when things go wrong. Who is accountable?
Okay, so beyond bias, there's the whole economic and societal impact. This is huge.
Massive. AI is poised to be a major disruptor. And there's a big productivity debate among economists right now. You've got optimistic forecasts. PricewaterhouseCoopers estimates AI could boost global GDP by up to 14% by 2030. That's huge. Like $15.7 trillion.
Wow.
Goldman Sachs predicts 7% over 10 years. McKinsey forecasts around $13 trillion additional output by 2030. They see big gains from productivity, automation, new products.
But not everyone agrees.
No. Other economists, like Darren Acemoglu at MIT, are more cautious. He argues that while many tasks are exposed to AI, maybe only 5% can be profitably automated soon due to costs, implementation challenges, organizational friction.
So a much smaller boost
Fuck
initially,
that.
like 1% GDP over a decade.
That's his perspective. It suggests the huge productivity transformation might take longer than the hype implies. It's a complex picture.
What seems pretty clear, though, is the labor market disruption.
Undeniable. The IMF did an analysis, found almost 40% of global jobs are exposed to AI, rises to 60% in advanced economies.
And it's not just blue-collar jobs this time.
No, that's the key shift. AI's ability with language, patterns, it's impacting high-skilled, white-collar jobs too. Writers, analysts, coders. The impact looks twofold. Some job replacement, where AI takes over tasks humans do now, potentially lowering labor demand in some areas.
But also augmentation.
Yes, probably more significantly in the near term. Job augmentation. AI is a powerful tool complementing human workers, enhancing productivity, freeing people up for more complex, creative, strategic work.
So AI isn't just taking jobs, it's potentially creating superpowers for workers who can adapt.
That's a great way to think about it, but it leads to a major concern.
Inequality.
Yes, the risk of growing inequality. The benefits might not be shared equally. First, between nations. Advanced economies with better infrastructure, more skilled workers, they're better positioned to harness AI. Developing countries might fall further behind, widening the global gap.
And within nations, too.
Absolutely. A potential polarization. Workers who can leverage AI might see their wages soar. Those whose jobs are easily automated might get left behind. Widening income gaps, potentially increasing social tension.
So what does this all mean for us?
It means this isn't just a tech challenge, it's deeply societal.
Right.
Policymakers need to be thinking hard about comprehensive social safety nets, robust retraining programs, lifelong learning initiatives. Ensuring this transition is as inclusive as possible. It needs careful management and foresight.
The toolkit. Mathematics and programming foundations.
Okay, so we've covered the history, the definitions, the ethics, the societal impact, a lot of the what and why. Now, let's shift gears. Let's talk about the practical foundations. How do we actually build these things?
Right. Moving from philosophy to the toolkit.
Exactly. And let's be clear, AI is not magic. It's a discipline built fair and square on the rigorous, elegant principles of mathematics, and then brought to life through computer programming. We'll use that first principles approach here. Really understand how AI works under the hood.
Mm-hmm.
Because mastering these fundamentals It's not just a formality. If we connect this to the bigger picture, it's the most critical step to truly understanding AI. It's the bedrock.
Okay, let's unpack this. Why do we need math? For some people listening, math might sound intimidating in this context, but I guess you could think of math as AI's native language, right? The fundamental way it perceives and processes the world.
That's a perfect analogy, yes. Math provides the framework for representing data, the tools for learning from it, and the methods for handling uncertainty. And there are three key mathematical areas where a deep, intuitive grasp is, frankly, non-negotiable if you're serious about this. First up, linear algebra, the mathematics of data. At its heart, machine learning is about processing huge data sets. Linear algebra gives us the tools to represent and manipulate all that data efficiently. Remember, all data, customer info, image pixels, words, eventually gets turned into numerical arrays. Vectors, matrices, tensors. Linear algebra is the grammar for working with these.
So vectors and matrices.
Fundamental. A vector could represent one data point, like a single customer's features. A matrix could hold an entire data set or maybe a grayscale image. Tensors are just generalizations of matrices to more dimensions. They're the basic data structure in deep learning frameworks like TensorFlow and PyTorch.
Like Lego bricks. Vector is one brick, matrix is a flat plate, tensor is a 3D structure.
Exactly like that. And operations like matrix multiplication, that's not just theoretical, it's the core operation in neural networks. Passing data through a layer, it's basically matrix multiplication. And concepts like eigenvalues and eigenvectors, they sound abstract, but they're key to techniques like principal component analysis, which we'll touch on later. They help find the most important directions or patterns in your data.
Okay, linear algebra for data structure. What's next?
Calculus, the mathematics of learning.
Calculus.
The old friend.
If linear algebra handles the data, calculus handles the learning, the optimization. Training an AI model, fundamentally, it's an optimization problem. We want to find the model parameters, the weights, that give the lowest possible error on our data. Calculus gives us the tools for that search.
How so?
Well, derivatives and gradients are key. A derivative measures the rate of change. In AI, we use it to see how tweaking a single parameter, like one weight, affects the overall error. A gradient is just a vector of all those derivatives. It points in the direction where the error increases fastest.
So to minimize error, you go the opposite way.
Precisely. That leads directly to gradient descent, the absolute cornerstone optimization algorithm for training most models. The idea is simple. Calculate the gradient, then take a small step in the opposite direction. Repeat.
Like walking downhill in fog. You check the slope where you are, take a step down the steepest path you can feel. Perfect analogy. That's exactly it. Trying to find the bottom of the valley, the minimum error, and the chain rule from calculus. That's the mathematical engine behind backpropagation, the algorithm that lets us efficiently calculate those gradients, even in deep, multi-layered networks. It's what makes large-scale learning feasible.
Okay, data structure learning. What's the third leg?
Probability and statistics, the mathematics of uncertainty.
Right, because AI predictions aren't usually absolute certainties.
Rarely ever. AI models operate in a world of uncertainty. They make predictions based on probabilistic reasoning. Stats gives us the framework to quantify and handle that uncertainty. Key concepts. Probability distributions, which describe the likelihood of different outcomes. Used everywhere. Modeling data, modeling uncertainty and predictions. Bayesian inference, a powerful way to update beliefs or models parameters as new data comes in. It's the foundation for things like naive Bayes classifiers used in spam filters. And basic descriptive statistics mean median, standard deviation, essential for just understanding your data to begin with, and then for evaluating how well your model is performing.
Now, for someone learning this stuff on their own, that math can seem like a mountain. Are there good resources?
Absolutely. Excellent curated paths exist. MIT, OpenCourseWare, Khan Academy, they have fantastic resources, often explicitly linking the math concepts directly to AI applications, which really helps motivation and understanding.
Okay, so math is the language. What about the tools to actually write the AI code, the programming side?
Right. The AI community has pretty much converged on one main language and a set of core libraries. The language, overwhelmingly, is Python.
Python. Yeah, that seems ubiquitous in data science.
Yeah. It's the undisputed lingua franca. Why? Simple, readable syntax, great for beginners, but also a huge, mature ecosystem of libraries that provide powerful tools for very complex tasks. Basic Python proficiency is essential. And within Python, there are libraries you'll use constantly. NumPy and Pandas are foundational. NumPy gives you efficient multi-dimensional arrays, those tensors we talked about. Pandas provides data frames, these high-performance structures for loading, cleaning, manipulating data. You live in these libraries.
Okay, NumPy, Pandas for data wrangling. What about the actual machine learning algorithms?
For classical ML, so not deep learning, yet scikit-learn is the king. It offers a clean, consistent interface to a vast array of algorithms: classification, regression, clustering, dimensionality reduction, model evaluation. It's incredibly comprehensive and user-friendly.
And the deep learning stuff.
Yeah.
The neural networks.
That's where TensorFlow and PyTorch come in. They are the two dominant open source frameworks. TensorFlow from Google is known for its robust tools for deploying models into production. Its high-level API, Keras, makes building models very straightforward. PyTorch from Meta AI is often favored in research. It feels more Pythonic, more flexible maybe. Its dynamic computation graph can make debugging easier, building custom stuff more intuitive.
So which one should a beginner choose?
Honestly, both are excellent. You can't go wrong. For really understanding the fundamentals of how deep learning works, PyTorch's slightly more explicit style can be quite pedagogically transparent. Many find it a great starting point for that reason, but both are incredibly powerful and widely used.
Core paradigms, supervised and unsupervised learning.
Right, we've got the math, the code. Our toolkit is ready. Now let's explore the core ways machines actually learn, the main paradigms. We'll start with the most common one, supervised learning.
Right.
And the fundamental difference here compared to unsupervised learning, it's like having a teacher versus figuring things out on your own from unlabeled stuff.
That's a perfect way to frame it, yes. Supervised learning works by learning from labeled data. The teacher-student analogy holds up really well. Imagine the student is our model. The textbook is our data set. The textbook has practice problems. Those are the inputs. And crucially, it has the correct answers. Those are the outputs, the labels.
Okay.
The goal is for the student, the model, to learn the underlying principles from these examples so it can solve new problems it hasn't seen before, problems without the answers provided.
Makes sense. So what's the typical workflow?
It follows a pretty standard process. First, data collection and pre-processing. You gather relevant data that has both the input features and the correct output labels. Clean it up, get it ready. Second, splitting the data. This is vital. You divide your labeled data set into typically a training set and a testing set.
Why split it?
Because the model only learns from the training data. The testing data is kept completely separate, held back. It's used only at the very end for a final, unbiased evaluation of how well the model performs on data it's never encountered.
To see if it actually learned or just memorized.
Exactly. To check for generalization versus overfitting, which is just memorizing the training set. Third, model training. You feed the training data to your chosen algorithm. It iteratively adjusts its internal parameters, those weights we talked about, to minimize the difference between its predictions and the actual labels in the training set. And finally, model evaluation. You unleash the trained model on that held out testing set, measure its performance, see how well it generalized. And terminology-wise, the input variables are often called features or independent variables. The output variable you're trying to predict is the target or the label or the dependent variable.
Okay, so within supervised learning, you mentioned two main types of problems.
Broadly, yes. Classification and regression, they're like two sides of the supervised coin. The key difference is the kind of output you're predicting.
How so?
In classification, the goal is to predict a discrete categorical label. The output belongs to a fixed set of classes, like is this email spam or not spam? Is this tumor benign or malignant? Is this handwritten digit a 0, 1, 2, up to 9?
Finite categories.
Exactly. The model tries to learn a decision boundary in the data that separates the different classes.
And regression.
Regression aims to predict a continuous numerical value. The output can be, theoretically, any real number within a range, like predicting the price of a house in dollars, tomorrow's temperature in degrees Celsius, the future price of a stock.
So a number on a scale, not a category.
Precisely. The model tries to find the best fit line or curve that describes the relationship between the inputs and that continuous output. Although the line can be blurry, you can use a regression model to predict the probability of belonging to a class, then turn that into a classification by setting a threshold.
Okay, let's dive deeper into a specific algorithm. How about linear regression? Sounds fundamental.
It absolutely is the quintessential regression algorithm, a great starting point. It's used to model the linear relationship between a dependent variable, the target, and one or more independent variables, the features. The core assumption is simple. The relationship can be represented by a straight line, or a plane, or a hyperplane in higher dimensions.
So, like drawing the best straight line through a scatter plot of data points.
Exactly that image. For a simple case with one feature by one, the model predicts the target, y, using the equation. Y equals b plus w1 by 1. Here, b is the bias, basically the y-intercept where the line crosses the vertical axis. And w1 is the weight for that feature, essentially the slope of the line.
And training, it means finding the best b and w1.
Yes, finding the optimal values for the bias and all the weights, if you have multiple features, that make the line fit the training data points as closely as possible. How do we measure closeness? Usually with a loss function. The most common for linear regression is mean squared error, MSE. It averages the squared differences between the predicted values on the line and the actual values, the data points.
And you minimize that MSE using gradient descent.
Typically, yes. Gradient descent finds the weights and bias that result in the lowest MSE. And the linear regression can be simple, one feature, multiple, many features, or even polynomial, where you fit a curve by adding powers of features, but it's still linear in terms of the coefficients you learn.
Okay, that's linear regression. Now, for classification, you mentioned support vector machines, SVMs. They sound powerful.
They are very powerful and versatile, especially good for classification tasks, but can do regression too. The core idea for classification SVM is finding the optimal hyperplane that best separates the data points of different classes.
Hyperplane, just a fancy word for a decision boundary. Line in 2D, plane in 3D.
Exactly. Now, there might be many lines or planes that could separate the classes. SVM looks for the specific one that has the maximum margin. The margin is the distance between the hyperplane itself and the closest data points from either class.
Ah, the closest points matter most.
Critically, those closest points are called the support vectors. They literally support or define the position and orientation of the optimal hyperplane. The analogy often used is fitting the widest possible street between two neighborhoods, the classes. The support vectors are the houses right on the very edge of that street.
And a wider street, a wider margin is better.
Generally, yes. A wider margin tends to lead to better generalization. The model is more likely to classify new unseen points correctly because the boundary is further away from the existing examples.
But what if the data isn't perfectly separable by a line? Real-world data is messy.
Great question. That's where the soft margin SVM comes in. An SVM trying to find a hard margin insists on perfect separation. No points misclassified, none inside the margin. A soft margin SVM relaxes this. It allows some points to be misclassified or fall within the margin. It introduces a penalty for these errors, creating a trade-off. Maximize the margin width versus minimize the classification errors. Much more robust for noisy real-world data.
Okay, that handles noise. But what if the fundamental relationship isn't linear? What if you need a curve to separate the classes?
This is where the real magic of SVMs comes in, the kernel trick. The idea is brilliant. It's 3D landscape. Suddenly, you might be able to slice through with a flat plane, a linear separator in 3D that perfectly separates the lifted points from the ones still on the table.
Okay, I can visualize that. But calculating coordinates in like a million dimensions sounds computationally impossible.
It would be. That's the trick. The SVM algorithm, using kernel functions, can find the optimal separating hyperplane in that high-dimensional space without ever actually computing the coordinates of the points in that space.
Whoa. Ow.
It uses a kernel function, like polynomial radial basis function, that calculates the relationships, the dot products, between pairs of points as if they were in the higher dimension. You get the result it needs, the optimal boundary, without the explicit, costly transformation.
That is clever. Finding a simple solution in a complex space without actually going there.
It's a beautiful mathematical shortcut. Makes SVMs incredibly powerful for complex nonlinear problems, widely used in text classification, image recognition, bioinformatics.
Unsupervised learning. Finding hidden structure.
Okay, so we've thoroughly covered supervised learning, learning with a teacher, with labeled data. Now let's shift to the other major paradigm, unsupervised learning. Here, the algorithm gets data without any labels, no correct answers provided. Its task is much more open-ended, discover hidden patterns, structures, relationships within the data, all on its own.
Like being handed that big pile of mixed Lego bricks we talked about, no instructions, just sort them somehow, find the groups.
Exactly. That's the core idea.
Which sounds challenging because how does it know if it did a good job? There's no right answer to compare against.
That's the inherent challenge. Defining success is often subjective, context dependent.
But the payoff is huge, right? Because most data in the world is unlabeled. Emails, articles, images, sensor readings.
Precisely. The ability to extract insights, from vast amounts of raw, unstructured data is incredibly valuable. That's the power of unsupervised methods. And they're typically used for two main kinds of tasks. First, grouping similar things together, that's clustering. Second, simplifying the data by reducing the number of features, that's dimensionality reduction.
Okay, let's start with clustering, grouping the similar.
Clustering is all about partitioning a data set into distinct groups, or clusters. The goal is that data points within the same cluster should be very similar to each other based on some metric, and very dissimilar to points in other clusters. It's about finding those natural groupings hidden in the data.
Like a marketing team segmenting customers based on purchase history. Find groups of similar shoppers.
Perfect example. That allows for targeted strategies, or biologists grouping genes with similar expression patterns, or astronomers finding clusters of galaxies. Lots of applications.
And the most famous clustering algorithm is?
Probably k-means clustering. It's popular because it's relatively simple, efficient, and easy to understand. Its main objective is to minimize the within cluster sum of squares, WCSS. Basically, it tries to make the clusters as compact and dense as possible. Points should be close to their cluster's center.
How does it work? Is it iterative?
Yes, it's an iterative process, often called Lloyd's algorithm. First, initialization. You, the user, have to specify k, the number of clusters you want to find. The algorithm then randomly picks k initial starting points as the first centroids, the centers of the clusters. Second, the assignment step. Each data point in your data set is assigned to the cluster whose centroid is nearest to it, usually based on Euclidean distance. Third, the update step. The centroid of each cluster is recalculated. How? By taking the mean, the average position, of all the data points currently assigned to that cluster. The center moves to the middle of its assigned points.
And then repeat.
Exactly. Repeat the assignment and update steps until the centroids stop moving significantly, meaning the clusters have stabilized.
But how do you choose k, the number of clusters? That sounds critical and maybe arbitrary.
It is critical and often requires some experimentation and domain knowledge. A common heuristic is the elbow method. You run k-means for several different values of k, say k1, 2, 3, 10. For each k, you calculate the total WCSS. Then you plot WCSS against k. Typically, the plot looks like an arm. WCSS decreases rapidly at first as you add clusters, but then the improvement slows down, forming an elbow shape. The k value at that elbow point is often considered a good choice. It's where adding more clusters gives you diminishing returns in terms of compactness.
Okay, that makes sense. So that's clustering. What about the other big use case? Dimensionality reduction, taming the curse.
Right. Dimensionality reduction.
Mm.
Many real-world data sets are high dimensional. They have lots and lots of features, sometimes thousands or even millions. Think genetics or image pixels.
And more features isn't always better. The curse of dimensionality.
Exactly. It sounds counterintuitive, but too many features can cause problems. As dimensions increase, the data becomes incredibly sparse. Points are very far apart from each other. This makes it much harder for algorithms to find meaningful patterns. Everything looks equidistant. It also increases computational cost dramatically, makes models much more prone to overfitting the training data. That's the curse.
So dimensionality reduction is the antidote. How does it work?
It's a set of techniques for transforming data from a high dimensional space down to a lower dimensional space. But crucially, while trying to preserve as much of the important information or structure from the original data as possible.
Yeah, do that.
Several reasons. Visualization is a big one. Humans can't easily visualize data beyond 2 or 3 dimensions. Reducing dimensions allows us to plot and explore complex data visually. It can also improve model performance by removing noise and redundancy, focusing the model on most important signals. And it reduces computational cost and memory requirements.
Like taking a complex high-res photo and making a simpler, smaller silhouette that still clearly shows the main subject.
That's a great analogy. Capture the essence, but in fewer dimensions. And the workhorse algorithm for this, the most widely used technique.
Let me guess. PCA. Principal Component Analysis.
You got it. Principal Component Analysis, PCA. PCA's objective is to find the directions in the data where the variance is maximal. These directions are called the principal components. It then projects the original data onto a new lower dimensional subspace formed by these top principal components. The process involves a few steps. Usually, you first standardize the data so features are on the same scale. Then you compute the covariance matrix to see how features vary together. The core step is eigendecomposition of the covariance matrix. This finds the eigenvectors, which represent the directions of the new axis, the principal components, and the eigenvalues, which tell you the amount of variance captured by each eigenvector.
So you pick the eigenvectors with the biggest eigenvalues.
Exactly. You sort them by eigenvalue, variance explained, and select the top k eigenvectors to form your new lower dimensional feature space. You then project the original data onto these k components.
Okay, now, it feels like we've talked about supervised and unsupervised learning as totally separate things. Do they ever work together?
Oh, absolutely. It's a common misconception to see them as isolated. In practice, they have a very powerful symbiotic relationship.
How so?
Unsupervised learning techniques, especially dimensionality reduction and clustering, are frequently used as a critical pre-processing step before applying supervised learning.
Ah, using unsupervised methods to improve the data for a supervised model.
Precisely. Imagine you have a data set with thousands of features. Training an SVM classifier directly might be slow and prone to overfitting because of the curse of dimensionality. But what if you first run PCA? Reduce those thousands of features down to, say, 50 principal components that still capture 95% of the original variance.
Then you train the SVM on those 50 components instead.
Exactly. And very often, the SVM trained on this lower dimensional PCA representation will not only train much faster, but it might actually achieve higher accuracy on unseen data. Why? Because PCA potentially removed noise and redundancy, focusing the SVM on the core patterns.
So, unsupervised feature engineering leads to better supervised modeling.
That's a key insight and a very common workflow in applied ML. Understanding this interplay is crucial for moving beyond textbook algorithms to solving real-world problems effectively. They complement each other beautifully.
The dawn of deep learning. Neural networks.
Okay, now we get to the part that's really driven the current AI explosion, right? Deep learning and neural networks. This is the stuff behind those incredible image recognition results, the natural language understanding that feels almost human sometimes. This is where it gets really interesting, I think.
It really is the engine of modern AI advancements. The core idea behind artificial neural networks, ANNs, is quite literally inspired by the brain. Just like our brains have billions of interconnected biological neurons, an ANN is made of interconnected processing units called artificial neurons or nodes arranged in layers.
So what does a single artificial neuron do? Is it like a tiny brain cell?
Sort of. The simplest model is the perceptron. It does a few basic things. It receives inputs, each multiplied by a weight, representing connection strength. It calculates the weighted sum of these inputs. It then adds a bias term. Think of it as the neuron's own internal threshold or tendency to activate. And finally, this combined value is passed through a nonlinear activation function like sigmoid, ton, or the very common ReLU, rectified linear unit.
Why nonlinear? That sounds important.
Absolutely crucial. If everything was linear, a deep network would just collapse into a single linear transformation. The nonlinearity is what allows the network as a whole to learn complex, intricate, nonlinear patterns in the data. Without it, they wouldn't be much more powerful than linear regression.
Okay, so a neuron takes weighted inputs, adds bias, applies nonlinearity, like a little decision unit.
That's a good way to think of it. It collects weighted votes, adds its own opinion, bias, and then decides via the activation function whether and how strongly to fire or pass on a signal.
And these neurons are organized into layers.
Yes. Typically, you have an input layer, which just receives the raw data, like pixel values or word embeddings. Then one or more hidden layers. This is where the real computation, the feature extraction, happens. Having multiple hidden layers is what makes a network deep, hence deep learning. And finally, an output layer, which produces the model's final prediction, like a class probability or a numerical value.
So how does this whole network actually learn? How do the weights and biases get set correctly?
Through training, using an algorithm called backpropagation, combined with an optimizer like gradient descent, it works in a cycle. First, forward propagation. You feed an input example, say an image, into the input layer. The signals propagate forward through the hidden layers, neuron by neuron, until the output layer produces a prediction. Second, loss calculation. You compare the network's prediction to the actual correct label for that input. You calculate the error or loss using a suitable loss function, like mean squared error for regression or cross entropy for classification.
Okay, you made a guess, saw how wrong it was. Now what?
Now comes the magic, backpropagation. This algorithm efficiently calculates the gradient of that loss function with respect to every single weight and bias in the entire network. Using the chain rule from calculus, it propagates the error signal backward through the network, figuring out how much each connection contributed to the final error.
So it assigns blame, essentially.
Exactly. It determines how much to adjust each parameter to reduce the error. Finally, weight update. Using those calculated gradients, the optimization algorithm, usually some variant of gradient descent, updates all the weights and biases. Each parameter is nudged slightly in the direction that reduces the error.
Like that orchestra analogy. Forward pass is playing the piece, loss is hearing the mistakes, back propagation is the conductor pointing out who messed up and how. Gradient descent is the musicians adjusting their playing.
That is a fantastic analogy, yes. That cycle forward pass, loss, back propagation, update repeats for thousands or millions of training examples, iteratively tuning the network until it gets good at the task.
Now, you mentioned standard ANNs aren't great for images. Too many connections, overfitting.
Right. A standard fully connected network, where every neuron connects to every neuron in the next layer, becomes computationally massive and unwieldy very quickly with image data. A small 100 by 100 image has 10,000 pixels. The first hidden layer would need millions of weights. Impractical.
So we need specialized networks, like convolutional neural networks, CNNs for seeing.
Precisely. CNNs are a type of deep neural network specifically designed for processing grid-like data, especially images. They solve the problems of standard ANNs using two clever ideas: sparse connectivity and parameter sharing.
How do they work? What are the key layers?
The core building block is the convolutional layer. Instead of connecting every input pixel to every neuron, this layer uses learnable filters, also called kernels. A filter is just a small matrix of weights, for example, 3 by 3 or 5 by 5. This filter slides or convolves across the input image patch by patch. At each position, it computes a dot product between the filter weights and the image pixels under it. This produces a feature map, highlighting where the specific feature the filter detects, like a vertical edge, a horizontal edge, a corner, a patch of color, appears in the image.
And parameter sharing.
This is key. The same filter with the same weights is used across the entire input image. So the network learns to detect a feature, like a vertical edge, regardless of where it appears. This dramatically reduces the number of parameters compared to a fully connected layer.
Like tiny magnifying glasses, each looking for one specific pattern, scanning the whole image.
That's a great way to visualize it. After convolutional layers, you often have pooling layers, like max pooling. These reduce the spatial dimensions, width and height of the feature maps. This further reduces parameters, computation, and makes the detected features more robust to small shifts or distortions in the input image. Finally, after several convolutional and pooling layers have extracted increasingly complex features, the resulting high-level feature maps are typically flattened into a vector and fed into one or more standard fully connected layers at the end to perform the final classification.
And they learn features hierarchically. Simple stuff first, then complex.
Exactly. The early convolutional layers might learn to detect simple things like edges and corners. Deeper layers combine these simple features to recognize more complex patterns like textures, shapes, maybe eyes or noses. Even deeper layers might combine those to recognize entire objects like faces, cars, or cats.
Like building blocks, edges, shapes, object parts, objects.
Precisely. It's a very intuitive way for a network to learn about the visual world. CNNs are the backbone of most modern computer vision systems.
Okay, so CNNs for spatial data like images. What about sequential data? Text, speech, time series. Standard networks struggle with order, right? No memory.
Correct. Standard feed-forward networks, ANNs, CNNs, process each input independently. They have no inherent memory of past inputs. This is obviously a problem for sequences. To understand a sentence, you need to remember the words that came before. To predict stock prices, you need to know past prices.
So the solution is recurrent neural networks, RNNs. How do they handle sequences?
RNNs introduce a feedback loop. The key idea is the hidden state. At each time step, the RNN processes the current input element, like a word, along with the hidden state from the previous time step. The output it produces and the new hidden state computes are then influenced by this history. This hidden state acts as the network's memory, summarizing information from all previous time steps. The output hidden state from one step is fed back as input to the next.
So it keeps context.
Exactly. And crucially, the same set of weights is used at every time step. This parameter sharing allows the model to apply the same learned rules across different positions in the sequence.
Like reading a sentence word by word, but always keeping the previous words in mind to get the meaning.
That's the intuition. It allows RNNs to model dependencies between elements in a sequence. But simple RNNs have a notorious problem.
The vanishing and exploding gradient problem. Sounds dramatic.
It is a major limitation. When training RNNs using backpropagation, the error gradients have to be propagated backward through time through all their current connections. Due to the repeated matrix multiplications involved in the recurrence, these gradients can either shrink exponentially towards zero, vanishing, or grow exponentially towards infinity, exploding.
And vanishing gradients are particularly bad.
Very damaging. If the gradients vanish, the network effectively stops learning from earlier inputs. It becomes impossible to learn long-range dependencies, relationships between elements far apart in the sequence. The memory becomes too short-term.
Like that game of telephone. The message gets lost over a long line.
Perfect analogy. The error signal just fades away or gets distorted.
So how do they fix this? More advanced RNNs.
Yes. The most successful solutions are LSTM, long short-term memory networks, and GRU, gated recurrent unit networks. LSTMs were specifically designed to combat vanishing gradients. They use a more complex recurrent unit with internal gates. They have a cell state, which acts like a conveyor belt for long-term memory, running straight down the sequence. And then they have 3 gates: an input gate, a forget gate, and an output gate.
Gates, like controlling information flow.
Exactly. These gates are small neural networks themselves, and they learn what information to allow into the cell state, what information to remove or forget from the cell state, and what part of the cell state to use for the output at the current time step. This gating mechanism allows LSTMs to selectively maintain and access information over very long sequences, effectively overcoming the vanishing gradient problem.
In GRUs.
GRUs are a slightly simpler, more recent variant of LSTM. Often, they perform comparably to LSTMs, but are a bit more computationally efficient.
Okay, that specialization, CNNs for space, RNNs, LSTMs for time, seems really important.
It leads to a profound concept in deep learning: the principle of inductive bias.
Inductive bias, what's that?
It means that these specialized architectures, CNNs, RNNs, aren't just random designs. They succeed because they have built-in assumptions about the nature of the data they're meant to process. A CNN has a spatial inductive bias. Its structure, local filters, pooling, parameter sharing, assumes that patterns in images are local and that a feature is useful regardless of where it appears, translation variance. An RNN-LSTM has a temporal or sequential inductive bias. Its recurrent structure assumes that the current element depends on previous elements in the sequence.
So instead of making a generic network learn these properties from scratch, which would be hard,
these specialized architectures encode those fundamental assumptions directly into their design. This makes them vastly more efficient and effective for their specific tasks, vision sequences, because they start with the right structural priors. It's a really deep insight into why these architectures work so well.
State of the art, advanced architectures and paradigms.
Okay, we've covered the workhorses, ANNs, CNNs, RNN, SLSTMs. Now let's get to the really cutting edge stuff: the architectures and paradigms defining the state of the art today.
Right. For years, as we said, LSTMs and GRUs were dominant for sequence tasks like language translation or text generation. But they had that inherent limitation, the sequential processing. Information had to flow step by step, making it hard to capture very long dependencies perfectly. And critically, it couldn't be easily parallelized on GPUs, creating a bottleneck for training really massive models.
So something needed to change to unlock the next level.
Exactly. And that change came in 2017 with a landmark paper from Google researchers. The title itself was revolutionary. Attention is all you need. It introduced the transformer architecture.
The transformer. This is the basis for models like GPT.
Right. It is. The transformer completely did away with recurrence, like in RNNs and convolutions, like in CNNs, for sequence processing. It relied entirely on a mechanism called self-attention. This single innovation solved the key problems of RNNs and unleashed the current era of large language models, LLMs. What's fascinating here is how this wasn't just an incremental improvement, it fundamentally changed the game.
So this self-attention mechanism, how does it work? You mentioned it's like shining a spotlight.
That's a good analogy. Instead of processing word by word, self-attention allows the model to look at the entire input sequence at once. Then for each word, it calculates attention scores that weigh the importance of all other words in the sequence for understanding the context of that specific word. It creates direct connections between every word and every other word.
So it figures out which words are most relevant to the current word, no matter how far apart they are.
Precisely. The process, simplified, involves turning words into numerical embeddings, vectors, adding positional information, since there's no recurrence to convey order. Then for each word, it learns 3 vectors: a query, Q, a key K, and a value V. Think of Q as, what information am I looking for? K is like a label on another word. Here's the kind of information I have. V is the actual content or meaning of that other word.
Okay, QKV.
The model calculates attention scores by matching the query of the current word with the keys of all other words using dot products. These scores are scaled and normalized using softmax to represent weights. The final output for the current word is then a weighted sum of the values of all words, where the weights are those attention scores. It blends information from the most relevant parts of the sequence.
And they use multi-head attention.
Yes, they run this self-attention process multiple times in parallel, each with different learned QKV projections. Each attention head can learn to focus on different types of relationships, syntactic dependencies, semantic similarities, etc. The results are then combined.
So what are the big advantages over RNNs that made transformers so revolutionary?
Two main ones, really transformative. First, parallelization. Because attention calculates relationships between all words simultaneously, not sequentially, the computation can be massively parallelized on GPUs. This drastically cut training times and made it feasible to train models on enormous data sets, which turned out to be key for LLM performance.
Unlocking scale.
Exactly. Second, superior handling of long-range dependencies. In a transformer, the path length between any two words is effectively one step. Through the attention mechanism, they're directly connected. In an RNN, the path length grows with the distance between words. This direct connection allows transformers to capture relationships between words far apart in a text much more effectively than even LSTMs.
So it wasn't just better, it was a different way of processing, parallel and relational, not sequential.
That's the fundamental paradigm shift, and it was the main technical catalyst for the scaling revolution we're seeing now.
Okay, transformers revolutionized sequence modeling. What about learning through interaction? Trial and error. That sounds like reinforcement learning. RL.
That's right. RL is a whole different paradigm. Not supervised, no labels. Not unsupervised, not just finding patterns. It's about learning optimal behavior through interaction. The framework involves an agent, the learner, like a robot or game player, interacting with an environment, the world, the game.
How does that interaction work?
It's a loop. The agent observes the current state of the environment. Based on the state, it chooses an action. The environment transitions to a new state as a result of that action, and critically, it gives the agent a reward or penalty, a numerical signal indicating how good that action was in that state. The agent's sole goal is to learn a strategy called a policy that maximizes the total cumulative reward it receives over the long run, not just the immediate reward.
Like training a dog. Dog is the agent, house is the environment, sit is an action, getting a treat is the reward. Goal. Learn actions that lead to the most treats over time.
Perfect analogy. That's exactly the principle. Key concepts in RL include the policy, the agent strategy, mapping states to actions, the value function, estimating the long-term value or desirability of being in a certain state, and the crucial exploration versus exploitation dilemma. The agent has to constantly balance exploiting the actions it currently knows lead to good rewards versus exploring new or seemingly random actions to potentially discover even better rewards it doesn't know about yet.
Finding the right balance seems tricky.
It's one of the core challenges in RL. There are also distinctions like model-based RL, where the agent tries to learn a model of the environment's dynamics, versus model-free RL, learning the policy or value function directly from experience.
And where is RL used? Games.
Games are a famous application mastering, go with AlphaGo, Atari games, but also robotics, training robots to walk, grasp objects, optimizing complex systems like traffic flow or chemical reactions, autonomous driving. Anywhere an agent needs to learn sequential decision-making in an environment.
Okay, so transformers handle sequences, RL handles actions. What about creating entirely new things? That brings us to generative AI. So what does this all mean? It means AI isn't just about understanding or predicting anymore, it's about creating.
Exactly. Generative AI marks a major shift. Traditional AI, often called discriminative AI, learns to distinguish between categories or predict values based on input data. The example, classify an image as cat or dog. Generative AI models, on the other hand, learn the underlying patterns and distribution of the data they're trained on, and then use that knowledge to create new original content that resembles the training data.
So generating new text, images, music, code.
All of the above. It's moving beyond analysis to synthesis. Several key techniques power generative AI. We've already mentioned transformer-based models like GPT, which excel at text generation by predicting the next token based on context using self-attention. Another very influential architecture, especially for images, was generative adversarial networks, GANs.
The counterfeiter and the detective analogy.
That's the one. GANs have two networks. A generator that tries to create realistic synthetic data, for example, fake images, and a discriminator that tries to distinguish between the generator's fakes and real data from the training set. They train together in a competition. The generator gets better at fooling the discriminator, and the discriminator gets better at catching fakes. This adversarial process pushes the generator to produce increasingly realistic outputs.
Clever. What else?
Variational autoencoders, VAEs, are another approach. They consist of an encoder that compresses input data into a lower dimensional latent space representing the core features, and a decoder that reconstructs the data from that latent space. To generate new data, you sample points from the latent space and feed them to the decoder. And more recently, diffusion models have become state of the art, especially for high fidelity image generation.
How do they work? The denoising analogy.
Exactly. They start with pure random noise and then learn to gradually reverse a diffusion process, iteratively removing noise over many steps, often guided by a condition like a text prompt, a photo of an astronaut riding a horse. By carefully removing the noise, they can sculpt the randomness into a coherent, high-quality sample matching the prompt. It's like taking TV static and precisely cleaning it up until a perfect image emerges, based on your idea of what it should be.
So the goal of all these generative techniques?
Fundamentally, to augment and automate creative and cognitive tasks. Applications are exploding. Content creation, articles, marketing copy, scripts, images, music, code generation, personalization, unique product recommendations, virtual try-ons, healthcare, drug discovery simulation, generating synthetic medical images for training, software development, auto-completing code, debugging, creating realistic simulations for training. It's transforming many fields.
From theory to practice, end to day.
A lifelong journey.
Wow, that's an amazing tour through the state of the art. But theory is one thing. To really get AI, you need to roll up your sleeves and build stuff right. Get your hands dirty. Absolutely essential. Moving from theory to practice is where the deeper understanding happens. And that AI self-study course outline we mentioned, it actually suggests some great first projects guiding you through the process.
Like what?
Well, for a beginner classification project, sentiment analysis of product reviews is classic. You build a model using NLP techniques to classify text reviews as positive, negative, or neutral. Teaches you text pre-processing, basic classification models. For computer vision, the hello world is handwritten digit recognition on the MNIST dataset. You build a CNN to identify digits 0 through 9. It's satisfying because you can achieve really high accuracy relatively quickly.
Okay, those sound like good starting points. Anything more intermediate?
Sure. Building a movie recommendation system using a dataset like MovieLens. You'd explore techniques like collaborative filtering, finding users similar to you, or matrix factorization to suggest movies a user might like based on past ratings. That gets into embeddings and recommendation concepts.
And for people who want to practice more, compete, learn from others. You mentioned Kaggle earlier.
Yes, Kaggle is an invaluable resource. It's an online platform, competitions, data sets, cloud notebooks. You can learn a ton just by studying the public notebooks, where people share their code and analysis for different problems.
And they have beginner-friendly competitions.
They do. The Titanic Machine Learning from Disaster competition is specifically designed for newcomers. You predict survival based on passenger data. It's a great way to get started with a real data set and see how others approach it. A key lesson you learn quickly on Kaggle is that practical AI isn't just picking an algorithm, it's about the whole cycle. Exploring data, cleaning it, engineering good features, trying different models, evaluating carefully.
Feature engineering, that often makes the biggest difference.
Very often. A simple model with well-engineered features frequently beats a complex deep learning model fed raw data. Data quality and thoughtful feature creation are paramount. It really grounds you in the practical realities. And just to show how these concepts merge, we can briefly look at AI in robotics. It's a field where perception, learning, and action all come together.
Building intelligent machines that interact with the physical world.
Exactly. The goal is autonomous machines that can perceive their environment, make decisions, and act. Key AI techniques are critical. Computer vision for seeing navigation, object recognition, guiding movements. Machine learning, especially RL, for teaching motor skills like walking or grasping through trial and error. Predictive maintenance for the robot itself. NLP for natural human-robot interaction, understanding commands, giving feedback.
Applications are everywhere. Manufacturing, healthcare.
Manufacturing, assembly, quality control, healthcare, robotic surgery assistance, transportation, autonomous vehicles, logistics, warehouse automation, space exploration, disaster response. The integration of AI is what makes modern robotics possible and so powerful. It shows how supervised learning, perception, RL action, and NLP communication combine to create truly intelligent systems.
Okay, so we've covered history, theory, tools, practice. What does this all mean for you, the listener, as you continue your own deep dive into this rapidly changing field? It feels like you need to be a lifelong learner.
You absolutely do. The pace of innovation in AI is just breathtaking. State of the art models from a few years ago might be baseline models today. So the learning never really stops, but the key isn't necessarily to chase every single new model, the model of the week. That's exhausting and inefficient. The real skill is learning to identify the underlying trends, the fundamental paradigm shifts.
How do you do that? How do you stay afloat in this constant flood of new papers and models?
Well, this raises an important question. How do you filter the signal from the noise? If you look back at the history, the truly impactful breakthroughs are usually those that introduce a new, powerful, and more general abstraction or architectural principle. Think about it. LSTM wasn't just a slightly better RNN, it introduced the general idea of gating to control information flow. That was the core concept. The transformer wasn't just a faster sequence model, it introduced self-attention, a general mechanism for relational processing. That core idea has since been applied not just to language, BERT GPT, but now to computer vision, vision transformers, reinforcement learning, even generalist agents like DeepMind's Gato.
So focus on the fundamental mechanisms that enable the new capabilities.
Exactly. Focus on understanding the foundational papers that introduce these new generalizable mechanisms. Follow the top tier conferences like NeuriPS, ICML, ICLR, where these big ideas are often first presented and debated. Because if you understand the core principle of self-attention, for example, you're equipped to quickly grasp the dozens or hundreds of models built upon it. This strategy, learning the fundamental building blocks rather than trying to memorize every specific structure built from them, that's the most durable, most efficient path to continuous learning and lasting expertise in this incredible, ever-evolving world of artificial intelligence. It's about understanding the first principles behind the progress.
Outro. What an incredible journey today. Seriously, from those ancient dreams of automatons right up to the bleeding edge of generative AI. We covered the birth of AI, the winters, the comebacks, the whole roller coaster. We defined the AI spectrum: weak, strong, super. We tackled the crucial ethics bias, fairness, transparency, and the huge societal and economic shifts AI is driving.
And we really dug into the toolkit, didn't we? The essential math, linear algebra for data, calculus for learning, probability for uncertainty, the power of Python and its core libraries.
Then the learning paradigms: supervised learning classification versus regression, deep dives into linear regression and SVMs with that clever kernel trick, and unsupervised learning clustering with k-means, dimensionality reduction with PCA, and how they work together.
And finally, the deep learning revolution, breaking down neural networks, the power of CNNs for vision, RNNs, and LSTMs for sequences, then the game-changing transformer, the trial and error learning of RL, and that whole creative explosion with generative AI IGNs, VAEs, diffusion models. Hopefully drilling down into those core concepts, those first principles, sparks some of those aha moments for you. That's where the real understanding comes from.
We certainly hope this deep dive has given you a solid foundation and, more importantly, maybe fueled your curiosity to explore even further. This field isn't slowing down. Thank you so much for joining us on the deep dive. Until next time, keep exploring, keep learning, and definitely keep asking the big questions.
Okay, that's it. Any questions? Any questions at all? All right. Well, this has been Military Industrial Museum. Please check out my channel. Got a lot of original music and anime cartoons and stuff, and a lot of military themed data and stuff. So check it out. All right. We are gonzo. Unless there's any questions, we're going to be gone. All right. Shut down.